Hence, in previous class, we solved the problems for shear stress for rectangular, circular, and I section. In this case also, in example 4, we're solving the problem for I section B, in which the shear stresses to various points and distribution of shear stress across the I section. We are going to solve this problem. Example 4, an I section is having overall depth 550 mm and overall width 200 mm. The thickness of flanges is 25 mm, whereas thickness of web is 20 mm. If the section carries a shear force of 45 kilonewtons, then find the shear stress at different points and stress distribution diagram. Draw the stress distribution diagram. This is the given figure, I section figure having the overall depth 550 mm and width is 200 mm. It's mistakenly is 20 mm, but in the it is not 20 mm. It is given in the figure is 200 mm. Overall width is 200 mm, having the flanges thickness 25 mm and web thickness as 220 mm. This is the flanges having the red portion, the horizontal members are called the flanges, and this vertical portion is called the web. Web having the 20 mm thickness and flanges, both flanges having 25 mm thickness. In which the shear stress in this problem, the shear force acting on this section is 45 kilonewtons is given. We have to find this shear stresses at various points. Various different points means at the layers, at top layer, at the bottom layer of the top flange, that is at the junction of the web and the flange, and at the neutral axis, at the bottom junction, and at the bottom layer, extreme bottom layer. These are the different points across the section. We are going to find shear stress values in this problem. So let us look. Before going to find the shear stress values, we should know the moment of inertia of this section about neutral axis. Moment of inertia I value. How to find the I value, that is the moment of inertia about neutral axis, means by assuming the whole figure as a rectangle, for example, by drawing the lines at this place. This it is a rectangle with the breadth is 200 mm and height is 550 mm. From this rectangle, if you subtract these areas, these two areas, then we can get the I section. If you subtract the moment of inertia of these two areas from the whole moment of inertia, then we can get the moment of inertia of I section. So here I am written the formula that the values are I equal to 200. The overall breadth is 200, overall width is 550. Therefore, the moment of inertia about neutral axis of overall rectangle is BDQ by 12. 200 is the breadth, depth is 550, 550 cube by 12. This is the moment of inertia of whole rectangle about neutral axis. Minus the moment of inertia of these two shaded rectangles. How to find that? We should know the breadth of the shaded area. This is shaded area breadth is total 200 minus web thickness 220, therefore 180. 200 minus 20 is 180. 180 means is off of the 180 is this rectangle breadth, and off of the 180 is breadth, rectangle breadth is off of the 180. So off of the 180 means 90 and 90. So breadth of the one rectangle, shaded rectangle, is 90 and the height is 550 minus 25 of the top flange thickness, 25 bottom flange thickness, total 50. So 550 minus 50, That is the 500 is the height of the web. So 90 into 500 cube by 12 plus 90 500 cube by 12. So 90 plus 90 500 cube by 12 plus 90 500 cube by 12, total 180 into 500 cube by 12. So that much of moment of inertia we should subtract from the overall rectangle moment of inertia. So 180 500 cube by 12. So then we can get the moment of inertia of I section after subtracting the two rectangles, 89791 6666.7 millimeter power 4. This is the moment of inertia value in terms of millimeter power 4. After getting the moment of inertia of all this high section, one by one we are going to find the shear stress at different locations. First is, number one is shear stress at extreme layer of the upper flange. At extreme layer of the upper flange means this is the upper flange, this is the bottom flange, this is the web. So extreme layer of the upper flange means at this place. How much shear stress will be developed at this layer? So how to know this layer? By considering the EF layer at this place, there is no area beyond this. There is no area beyond this or above this to slide on this surface. Therefore, there is no area. Therefore, AY bar is also 0 at this layer. AY bar 0. Therefore, shear stress is also 0 at this layer, because formula is FAY bar by B into I. In this AY bar is 0 at this layer, because there is no area to slide on this surface. So that's why shear stress is 0 at the extreme top layer. And second, number 2 point, the shear stress in the upper flange, shear stress in the upper flange at the junction, at this place, at the junction of web and flange. Web and flange junction is this. By considering the layer EF at this place, by considering a layer EF at the junction, this is the layer, by applying this formula at that particular layer EF, FAY bar by B into I, by applying this formula at this layer EF, then we can find the shear stress tau value at EF layer. So in this, by considering the EF layer at this point, what is the area above the layer? Area above that layer is flange area. Area above this is flange area. So flange area is 20 into 25, 200 into 25. 200 is the breadth, 25 is the thickness, that is the area of the flange, 5000 mm square. Then what is the Y bar value at this place? Y bar value. What do you mean by Y bar value? I shaded is this at this place. Y bar means that formula. Y bar means the center of gravity distance of that area from neutral axis. So we are considering the layer at this place. Above this layer is area of the flange, 200 into 25, 5000 mm square, and Y bar means the center of gravity of this shaded portion from neutral axis distance. So how to get this distance? This total height from this place to this place, total height of the web is 500. This place to this place is off of the web distance is 250. It is the 250 mm distance. Plus this much distance is off of the flange is 12.5. Total 25 by 25. The center of gravity which will be located at the center of the rectangle, that is flange, upper flange. So off of the upper flange height is 12.5. So 250 plus 12.5, 262.5. Otherwise, from this place to upper flange distance is 275. 250 plus 25 minus 12.5. This is the 12.5 minus. Otherwise, we should know that Y bar value. So Y bar value is 262.5 mm. That is the center of gravity of the shaded area from neutral axis distance. Distance of center of gravity of shaded area from neutral axis. It is located in the diagram. So 262.5 mm. Dear students, remaining parameter in that formula, FA y bar by B into I, B value. What is the B? We are considering the breadth at this layer, EF layer. So what is the breadth of that EF layer is equal to 200 mm. Is equal to 200 mm. B is equal to 200 mm. We are finding the shear stress in this flange. Therefore, we should take the breadth of the flange itself is the B value. Then Fe is given in the problem 45 kilonewtons, 45,000 newtons. Then I value. Already we calculated moment of inertia of whole section about neutral axis 897916666.4 mm power 4. These are the values which are calculated at EF level. So by substituting these values into our equation, tau equal to FAY bar by B into I. F is the 45,000 newtons into AY bar, area is the 5,000, Y bar is 262.5 divided by B value is 200 mm, I value is 897916666.7. So upon calculation, the shear stress in the upper flange at the junction is 0.328 megapascals, 0.328 megapascals. Clear, students? So wherever you calculated the shear stress value, you should consider a layer at that particular fiber above which we should consider the area. So while calculating the AY bar, the area must be above the considered layer, and Y bar is the distance of that shaded area from the neutral axis. So remaining is shear force, and B is the breadth of the layer which is considered, at which we are going to find the shear stress, and I is the moment of inertia about neutral axis. Clear, student? This is the value of shear stress in the flange at this particular junction. Junction means the meeting point of the web and upper flange. Here also one junction is there, the meeting point of the web and bottom flange, another junction. So shear stress in the web. Now we are already calculated or find the shear stress at the junction in the flange. Now we are going to find the shear stress in the web at the same junction. Are you clear, students? Shear stress in the flange at the junction, one of the point, and the shear stress in the web at the same junction. Whenever you calculated the shear stress in the web at the junction, you should take the breadth of the layer is 20 mm, because this is the thickness of the web is 20 mm. You should take the breadth of the layer as 20 mm. So we are taking the layer at this point. Now EF is, this point is E and this point is F. So EF layer from this place to this place. Whenever you calculated the shear stress in the web, you should take the layer at this point, EF. So by applying the FA y bar by B into I formula at this EF level. So area means the area above the EF level. Area above the EF level is the same area, flange area you should take. Whenever this area which slides over the EF, the shear stress will be developed at the EF level. So area is same to 200 into 25, that is 5000 mm square. And Y bar is also same as in the previous case, 262.5, because the area which is above the layer EF having the distance of its CG from neutral axis is 262.5 mm. Now only change is B value. B is suddenly, breadth is suddenly changes from 200 mm to 20 mm. So B is taken as 20 mm here. The F is same value 45,000 newtons. And I value is same value 8979,166,666.7. So all are the same values as previous case, only except breadth. Breadth is suddenly decreases from 200 to 20 mm when we are calculating the shear stress in the web. Therefore, upon substitution of all the parameters into a given equation, FA y bar by B into I, we get 3.28 megapascals as shear stress in the web at the junction. Clear, students? The shear stress is suddenly changes from 0.328 to 3.28 megapascals from flange to web. Next, fourth point, shear stress in the web at the neutral axis. Shear stress in the web at the neutral axis. I already shaded in that diagram. We are going to find the shear stress at this place. Shear stress in the web at the neutral axis. So now the EF layer is at this place. You should consider the layer EF at neutral axis. This is the layer. So while you applying this formula FA y bar by B into I at this point at the neutral layer, AY bar in this formula is should be taken two areas. Here I shaded two areas above the level EF. Above the level EF or above the layer EF, we have two areas. These two areas. So AY bar is combinedly you should take for two areas. If one area is there, area and Y bar should be taken separately. Area and Y bar. So more than one area is there. If the more than one areas are there, you should consider the combinedly AY bar. AY bar means A1Y1 plus A2Y2. AY bar is the A1Y1 plus A2Y2. So A1Y1 means AY bar in place of AY bar, A1Y1 plus A2Y2. Here, what is the A1 area of the flange? What is the Y1? Y1 means the center of gravity of that A1 area from neutral axis distance. What is the A2? A2 is the area of the web. That is the web above the neutral axis. This is the A2. And Y2 means that particular A2 area having the CG distance is a rectangle off of the distance CG is there. The center or distance of this center of gravity from the neutral axis. This is the Y2. Okay. So A1Y1 plus A2Y2 is the AY bar for the given shaded areas. In that 200 into 25, 200 into 25 is the thickness of the flange, that is the A1, into 262.5 is the distance of its CG from neutral axis, plus A2Y2. A2 is the area of this half of the web. Half of the web height is 250, total web height is 500. 250 is this much height and 20 is the thickness of the web. 250 into 20 is the A2 area into Y2, A2 is the 250 into 20 into Y2 is the Y2 means center of gravity of this area from neutral axis. Total 250 height from neutral axis, the center of gravity distance is 125, 250 by 2, 125 mm. Okay, half of the 250. So 250 into 20 into 125 is the A2Y2. So A1Y1 into plus A2Y2 is becomes AY bar. So one calculation, AY bar is 1937500 millimeter cube. This is area is meter square, Y bar is the millimeter. Millimeter square, millimeter into millimeter cube. So the value of AY bar at the neutral axis is that. And B, breadth of this layer is 20 mm itself because thickness of the web is 20 mm. And F is same 45,000 newtons whole section and I is same whole section 8979,166,666.7 mm power 4. So these are the values at neutral axis. So upon substitution of all these values into FAY bar by B into I. F is 45,000, AY bar is the 1937500, divided by B is 20 mm, I is the 897916666.7. So after calculation, the value of shear stress is 4.85 megapascals. So shear stress at neutral axis is 4.85 megapascals, which is maximum value. So shear stress in the I section at neutral axis is maximum 4.85 megapascals in this problem. Clear, students? So remaining values, remaining means the shear stress at the bottom junction, shear stress in the flange at the bottom junction, shear stress in the web at the bottom junction, and shear stress at the extreme bottom layer. These are the three values are there by symmetry, because this diagram, this I section is symmetry about neutral axis. Wherever, whatever the values at upper junction, same values having will be developed at the bottom junction. Okay, so that's why I written that shear stress in the web at the bottom junction, at the junction of web and bottom flange. Shear stress in the web at the junction of web and bottom flange having the same by symmetry 3.28. Already we calculated that shear stress, this is the shear stress in the web at the junction of web and upper flange is 3.28, having the same value at the bottom junction. So by symmetry, tau equal to 3.28 megapascals. And also shear stress in the bottom flange, shear stress in the bottom flange at the same junction of web and flange is 0.328, is also calculated earlier. This is the shear stress in the web at the junction, and also shear stress in the upper flange, shear stress in the upper flange at the junction. So you should calculate at the junction 2 times. So shear stress in the flange at the junction 1 point, shear stress in the web at the junction is another point, and shear stress in the web at the bottom junction 1 point, and shear stress in the bottom flange at the junction is another point. So because of symmetry, these are taken as same values. By symmetry, tau equal to 0.328 megapascals as earlier calculated. And the last value, shear stress at the extreme layer of the bottom flange. Extreme layer of the bottom flange is also 0, because the area which is sliced over the bottom flange is completely sliced the overall area. There is no area containing below that extreme layer. Therefore, there is no sliding resistance force at that particular layer. Therefore, shear stress is 0 at the bottom, extreme bottom layer. Clear, students? These are the values of shear stress at different locations of I section. Like this, you have to calculate the shear stress values by applying the tau equal to FAY bar by P into I formula at different points. After calculating the values of shear stress at different locations, you should draw the shear stress distribution diagram across the I section. So by drawing the shear stress distribution, before drawing the shear stress distribution diagram, we should draw first I section again, total I section. From that I section, draw the horizontal lines, that is the tracing lines from the different locations. So at the extreme upper layer, at the junction, at the neutral axis, at the junction of bottom flange, at extreme bottom layer. At these points, 5 lines should be drawn from the different locations. These are the tracing lines. At that tracing, on the tracing lines, you should locate the shear stress values. So by drawing the adjacent to the I section, a vertical line. Draw a vertical line. On that vertical line, you should locate the points at extreme layers as 0 shear stress. At this point, 0 shear stress will be developed. Therefore, on that vertical line itself, you should locate the points. So from that point, at the upper junction in the flange, the shear stress value is 0.328 megapascals. So locate this point from on the line drawing from the junction. Okay, on the line drawing from the junction, you should locate the point as 0.328 megapascals. It is in the flange. And the shear stress in the web at the same junction. Shear stress in the web at the same junction means at the same horizontal line, you should locate the point at 3.28 megapascals from the vertical line. This is the distance 0.328 locate, and distance of 3.28 somewhere else randomly 3.28 megapascals locate on the same horizontal line. Okay, first of all draw the vertical line, and here 0 values, shear stress value 0, locate on the horizontal line, and locate 1.328, and the same horizontal line locate 3.28 megapascals, and at neutral axis locate from the neutral axis, draw a horizontal line and locate on that horizontal line 1 point which represents 4.8 megapascals, which is more than the 3.28. So up to this 3.28, locate another extreme point on the neutral axis 4.85 megapascals. So, and similar values as that of the upper junction, upper layers, you should locate at the bottom junctions and layer. So again, locate the point on the horizontal line from the bottom junction is 3.28, which is equal to upper layer, and 0.328 again 0.328 megapascals on the same horizontal line, and 0 at the bottom junction, bottom layer. So these are the points. After locating the points like this, you should join these points by parabolic curve, because the shear stress value changes across the rectangular portions as parabolic curve. So you should join this point as parabolic curve and horizontal line, parabolic curve, continuous parabolic curve, and horizontal line and parabolic curve from this place. Like this, you should draw the shear stress distribution diagram for the given I section. Clear, students? This is the shape of the shear stress distribution across the I section. I hope you are understanding. Practice once again. For the I section, it is the bigger problem, shear stress distribution problem. After calculating the values at different location of I section, we should draw the shear stress distribution diagram like this. The shape of the shear stress distribution diagram for I section is like this. First, locate the 0 shear stresses on the vertical line at extreme fibers, and at the junctions 2 values in the flange. While calculating the flange, while calculating the web, we should locate the shear stress values, 2 shear stress values at the junction. While calculating the flange, it is 0.328. While calculating in the web, it is 3.28 on the same horizontal line. So suddenly the shear stress values changes from 0.328 to 3.28 megapascals, because suddenly the breadth of the section is changes from 200 to 20 mm at the junction. And at the neutral axis, the shear stress value is 4.85 megapascals. And again, shear stress in the web at the bottom junction 3.28. And draw the horizontal line at the junction, and the shear stress values in the bottom flange at the junction is 0.328 megapascals. And shear stress at extreme layer of the bottom flange is 0. Like this, you have to draw the shear stress distribution by joining these points by parabolic curves. Okay. Let us go for the next problem. This is the T section. As you calculated in the I section, same in the T section, except at the bottom flange is absent here. It is having one upper flange and one web. but the neutral axis is not at the center for this T section. You should locate the neutral axis first. After locating the neutral axis only, you should calculate the moment of inertia about neutral axis. And after calculating the moment of inertia about neutral axis, then you can proceed to find the shear stress values at different locations by applying F tau equal to FA y bar by B into I formula. Let us look. Let us solve this problem in this class. Example 5. First of all, let me read the problem. A T section of a beam shown in figure is subjected to a shear force of 100 kilonewtons. F value is given in the problem itself. 100 kilonewtons. Find the shear stress at the junction and at the neutral axis. Also draw the stress distribution diagram across the section. So you should find the shear stress values at the junction and at neutral axis. And remaining two values, the shear stress at extreme top layer is 0. Shear stress at extreme bottom layer is 0. Always the extreme layers, the shear stress values at extreme layers are 0. So in this problem, we have to find the shear stress values at the junction. Means at the junction means we should find the shear stress in the flange at the junction, shear stress in the web at the junction, because these are meeting point. The shear stress values are different in the flange and the web at the junction, and shear stress at neutral axis. Okay, before going to proceed this problem, we should locate the neutral axis position. So distance of neutral axis from the bottom face. Distance of neutral axis. The neutral axis must be nearer to the flange, because the weight of the flange is more when compared the other side. Because other side there is no flange, the weight is moved towards the flange. Therefore, neutral axis is also very nearer to the flange. So first of all, locate the neutral axis distance from the bottom face. From this bottom face, this distance you should calculate. So to calculate this distance, the formula is distance of neutral axis from the bottom face. This is the y bar is equal to a1 y1 plus a2 y2 by a1 plus a2. This is a formula to locate the neutral axis or central axis from the bottom face. So a1 is the flange area, a2 is web area. a1 is 200 into 50 mm. 200 is the flange breadth and 50 mm is the thickness of flange. And 250 the overall height. Therefore, 250 minus flange thickness 50 mm. Therefore, height of the web is 200. So, height of the web is 200. Thickness of the web is 50 mm. This is the A2. So, Y1 means what is the Y1? Y1 is here the center of gravity of flange from bottom face. We are calculating the distance of neutral axis from the bottom face. You should take the Y1 from the bottom face itself. So from the bottom face, the center of gravity of flange. Center of gravity of flange is center of flange. So center of flange means from the top surface, it is 25 mm distance. So from the bottom surface, how much distance it is? Total 250 minus 25 subtraction. So after subtraction of 25 from 250, 225 is the distance of center of gravity of flange from neutral axis is 225. So 200 into 50 into 225. A1 is the 200 into 50. Y1 is the 225. Similarly, A2, Y2. A2 means the area of the web. Area of the web is also 200 into 50. Height of the web and thickness of the web is 50. And Y2 means the center of gravity of web from the bottom face. So total 200 height. The center of gravity of the web must be at the center, that is from the bottom face it is 100 mm. So 100 mm is the Y2. This is the A1 Y1 plus A2 Y2 from the bottom face divided by A1 plus A2. Both are same. A1 is the 200 into 50, A2 is also 200 into 50. Upon calculation of this location of neutral axis from the bottom face, it is 162.5 mm. So neutral axis which will be located from the bottom face is 162.5 mm distance. Okay, this is the height of the web is 200. 162.5 mm distance is the neutral axis distance from the bottom face. So after locating the neutral axis from the bottom face, find the moment of inertia of whole section about neutral axis. Moment of inertia whole section about neutral axis. How to find the new moment of inertia? Moment of inertia whole section about neutral axis is moment of inertia of flange about neutral axis, moment of inertia of this web about neutral axis. Two areas are there. Okay, separately we have to calculate the moment of inertia and the summing of their two, then we can get the whole moment of inertia. So this is the moment of inertia of flange about neutral axis, moment of inertia of web about neutral axis. So how to calculate the moment of inertia here? Moment of inertia of flange about its own CG. About its own CG is the formula BdQ by 12. BdQ by 12 means B is the breadth of the flange, D is the depth of the flange. Breadth is 200, depth is 50, 200 into 50 Q by 12 is the, what is the BdQ by 12? The moment of inertia of flange about its own CG. But we should know the moment of inertia of this flange about neutral axis. So how to calculate the moment of inertia about neutral axis means, first of all, find the moment of inertia of flange about its own CG and shift that moment of inertia towards neutral axis by using parallel axis theorem. Parallel axis theorem. Parallel axis theorem, the moment of inertia about neutral axis, according to the parallel axis theorem, moment of inertia about neutral axis is equal to moment of inertia about its own CG, okay, plus area, that is the flange area here, whatever the area we are going to consider, that area of that particular portion into y square. Y square means, this is the y means distance between two axes. Between them we are shifting the moment of inertia. Here two axes means these are the two axes, between distance between these two axes is y. So A is the area of the flange. This is the moment of inertia of any area about neutral axis. If we know the moment of inertia about its own CG, then we can calculate the moment of inertia about neutral axis by using this formula. This is the parallel axis theorem. So like that, moment of inertia of CG about its own CG is the 200 into 50 Q by 12, BdQ by 12, plus A is the 200 into 50. 200 into 50 is the area of the flange, into y square. Y is the distance between two axes. Here distance between these two axes is, how to calculate the distance? The distance from the bottom face, the distance of CG of flange from the bottom face is 225. Isn't it? Total 250. This is the 25. Center of gravity of flange from the upper layer is 25. So 250 minus 25 is the 225, the distance of flange CG from bottom face. But we know that the distance of neutral axis from the bottom face is 162.5 mm. So from this distance, we can subtract from 162.5 mm distance, then we can get the distance between two axes. So distance between two axes is 225 minus 162.5. This is the y value whole square. Clear, students? I clearly mentioned in the formula 225 minus 162.5 whole square is the y square. This is the moment of inertia of flange about neutral axis. Similarly, the moment of inertia of web about neutral axis, by using same formula, parallax theorem. So center of gravity, moment of inertia about center of gravity of the web. We know that BDQ by 12 again. Here the B is breadth of the web. Breadth of the web is 50 mm. D is the depth of the web. Depth of the web is 200 mm. So 50 into 200 cube by 12 is the moment of inertia about its own CG, ICG, plus area of the web is 200 into 50 itself. 200 into 50, that area kuda same, 200 into 50 into y square. What is y square here? Here y square means distance between two axes. What are those two axes? Center of gravity of the web and the neutral axis. This is the distance between two axes. So how to get these distance? The distance from the bottom face neutral axis is 162.5. Already we calculated here. From that you should subtract this distance. What is this distance? Center of gravity of the web from the bottom face is 100 mm. Total 200. Center of gravity is at a distance of 100. So 162.5 minus 100. Then we can get the distance between two axes. Clear, students? So 162.5 minus 100 whole square. That is the y square. This is the moment of inertia of web about neutral axis. Therefore, by summing of these two values, flange and web are combinedly together called the T section. Therefore, moment of inertia about neutral axis of whole section is 11,354,166.7 mm power 4. In terms of mm power 4, that is the moment of inertia of T section. Dear students, you have to remember this parallel axis theorem. You have to remind from your knowledge of engineering mechanics. There also we used the parallel axis theorem to calculate the moment of inertia about other axis if we know the moment of inertia about CG. Clear, students? So this is the parallel axis theorem. After calculating the moment of inertia, you should find the shear stress values at different locations. Here in this problem, shear stress value you should find. Shear stress at extreme upper fiber is 0. It's always 0. See, extreme layers shear stresses are 0. And shear stress in the flange at the junction, shear stress in the web at the junction, shear stress at neutral axis, shear stress at the bottom, extreme bottom layer. These are the values. So shear stress at extreme bottom layer is 0. Shear stress at extreme upper layer is 0. These two values are directly we can write as 0. And you should find the shear stress at the junction 2 times shear stress at neutral axis. So one by one, shear stress at extreme upper layer. Shear stress at extreme layer of the upper flange is 0 because since AY bar is 0. Here there is no area above this layer, therefore shear stress is 0. Next, shear stress in the upper flange at the junction of web and flange. Here I shaded the flange area. We should consider the layer at this point now. So we are calculating the shear stress in the flange at the junction means we should consider the layer at the junction. So this is the layer at which we are going to find the shear stress values by applying the FA y bar by B into I at this junction. So by applying the formula, in this formula we should know F value, AY bar value, B value and I value. Here one area is there, therefore A and Y bar are taken separately. What is the area? Area above this layer is flange area, 200 into 50. 200 into 50 is 10,000 mm square. Okay, and Y bar means, again Y bar here, center of gravity of flange shaded portion from neutral axis distance. Distance of that shaded area from neutral axis. Distance of center of gravity of shaded area from neutral axis is called the Y bar here. So here the distance of center of gravity from the bottom face is 225. From that, you should subtract the distance of neutral axis from the bottom face, 162.5. So 225 minus 162.5, we get 62.5 is the distance of center of gravity from neutral axis, 62.5 mm y bar. And B, what is the B value at this layer? B value is 200 mm. Breadth of the flange is 200 mm. And F is given in the problem 100 kilonewtons, 100 into 1000 newtons. And I also already calculated moment of inertia 11354166.7 mm power 4. These are the values at the junction while calculating the shear stress in the flange. So upon substitution of all the values, tau equal to F is 100 into 1000, area is the 10,000, y bar is 62.5, B value is 200 mm, I value is 11666.7 mm power 4. So upon substitution of all the values, we will get the shear stress is 2.75 megapascals in the flange. 2.75 megapascals in the flange at the junction. Clear, students? Next, third point, you should calculate the shear stress in the web at the junction itself. In the web at the junction, in the flange at the junction. So third point, shear stress in the web at the junction of web and flange. Again, apply FA y bar by B into I formula at the same junction, but in this case, we are calculating the shear stress in the web. While calculating the web, we should take the breadth of the web as 50 mm here in this formula. All are same values. We are considering the layer at this point. So in previous section, we consider the layer breadth is this much. Here we are considering a layer at this level, web in the web, EF layer. So you should substitute the breadth of the layer as 50 mm, that is the layer thickness of the web itself. So all are same values because the area above this layer is flange itself. Y bar is the distance of its flange CG from neutral axis. F and I same. So only the variable is 50 mm. Suddenly the breadth reduces from 200 to 50 mm here. So B is only the change in value after substitution of all the values except B. B is the 200 mm in the previous case, in this case 50 mm. So 100 into 1000 is the F value, area is the 10,000, Y bar is the 62.5, and I value is the 11354166.7, and B is in place of 200, substitute the B value as 50 mm here. Then we can get the shear stress in the web at the junction is 11 megapascals. Okay, shear stress in the web at the same junction. Shear stress in the flange at the junction is in the previous case calculated. Clear? Clear, students? The previous case, this is the 2.75 megapascals is the shear stress in the flange at the junction. This is 11 megapascals is the shear stress in the web at the junction. And finally, shear stress in the web at the neutral axis. Neutral axis is in the web itself. Therefore, shear stress at neutral axis. So again, apply this formula at the neutral axis. Apply this formula at the neutral axis. So upon applying the FA by bar by B into I at the neutral axis, we should consider the layer at neutral axis. Upon considering the layer at neutral axis, this is the E, layer EF. So we are considering the layer at this neutral axis. Neutral axis దగ్గర మనం layer consider చేస్తున్నాం. Neutral axis దగ్గర layer consider చేస్తున్నప్పుడు we should take the area above the EF layer. Above the EF layer having the areas, flange area is there, some amount of web area is there. So here I shaded that total area which is above the EF level. So two areas are there. We should consider AY bar combinedly. AY bar means A1Y1 plus A2Y2 as previous case. So A1Y1 means A1 is area of the flange. Y1 means the center of gravity of that A1 area from neutral axis. Okay, so 200 into 50 is the area of the flange, and distance of that CG from neutral axis is 225 minus 162.5. 225 is the distance from the bottom face, and 162.5 the distance of neutral axis from bottom face. So distance between these two axes is 225 minus 162.5. This is the A1 Y1. Okay, next A2 Y2. A2 Y2 means the small area is there above the EF level. This is the A2. A2, what is this distance from total distance? That is the total height of the web is 200, and this is the 162.5. 200 minus 162.5 is the height of this small portion of web. 200 minus 162.5, that is the 37.5. 37.5 is the height of the web, and thickness of the web is 50 mm. So area is 37.5 into 50, and Y2 means center of gravity of this small portion from neutral axis. So total height is 37.5. Center of gravity is located at the center. That means from the neutral axis, it is 37.5 by 2. So this is the A2, Y2, A1, Y1. Then we can get the AY bar for these two portions about neutral axis. So upon calculation of AY bar, 660,156.25 mm cube. That is the AY bar above the neutral axis. And B is the breadth of that layer which is considered that the neutral axis is 50. Here మనం ఇక్కడ కన్సిడర్ చేస్తున్నాం కాబట్టి దాని థిక్నెస్ ఏంటంటే 50 mm. లేయర్ ఇక్కడ కన్సిడర్ చేస్తాం. లేయర్ ఇక్కడ కన్సిడర్ చేసాం అనుకోండి, ఆ లేయర్ యొక్క బ్రెడ్త్ ఈస్ 200 mm అవుతుంది. ఇప్పుడు లేయర్ ఇక్కడే కన్సిడర్ చేసాం అనుకోండి, జంక్షన్ దగ్గర వెబ్ పోర్షన్ లో థిక్నెస్ ఇస్ 50 mm అవుతుంది. ఇక్కడ కన్సిడర్ చేసాం అనుకోండి, layer thickness is 50 mm. So B is changes continuously from layer to layer. So B is 50 mm at the neutral axis. F is 100 into 1000 newtons is given in the problem. I is also already calculated for the whole section 113541 So upon substitution of all the values, tau equal to F. F is the 100 into 1000 newtons. AY bar is combined we calculated for the two portions 660,156.25 divided by B is the breadth 50 mm divided by I value is 113541 So upon substitution and calculation of this shear stress value, we get 11.628 at neutral axis. 11.628 megapascals at neutral axis. Again, fifth point is shear stress at extreme bottom layer. Extreme bottom layer means at this place. If we consider the layer at this place, there is no area below this. Therefore, there is no sliding resistance force at this layer. Therefore, shear stress is 0 at the extreme layers. So, always you should mention the shear stress at extreme layers as 0. Okay, these are the shear stress values at different locations. After calculating all the values, draw the shear stress distribution. Shear stress distribution diagram like this. So, after calculating all the values, again draw the T section and draw the lines which is passing through the neutral axis, and at the extreme layer at the junction, draw the lines and locate the points by drawing the vertical line. First of all, draw the vertical line across the section, locate the 0 values on the vertical line at extreme layers, and shear stress value in the flange at the junction value is 2.75 megapascals. Shear stress in the web at the junction is 11 megapascals in the same horizontal line, because these are the two points at the same junction, but one is in the flange, another one is in the web. Suddenly the breadth is changes from 200 to 50 mm. That's why the shear stress increases from 2.75 megapascals to 11 megapascals, and the shear stress at the neutral axis is 11.628. Greater than the 11 megapascals. That's why we are locating far away from the vertical lines, 11.628 megapascals, and shear stress at the bottom junction, bottom layer is G. So how to join these points from 0 to 2.75 parabolic curve? 2.75 to 11 is horizontal line, because these are the developed at the same junction, and 11 to 11.628 is the parabolic curve, and that will be continued. The parabolic curve continues to up to 0. So this is the whole 0, 11.628 and 11. This is the continuous parabolic curve. Okay, like this you have to draw the parabolic curve from different points, and we get the shear stress distribution diagram across the T section. This is the shape of the shear stress distribution across the T section. Clear, students? So let us close this class up to now. Let us look another problems, another different problems, T section problems. One or two problems are there in the shear stress chapter. After that, we can close this chapter and we can go for unit 4. Okay, students, bye.